In question 2a part 1, we have a crane using 4 identical cables to lift a container of mass 22,000 kilograms. We need to assume that the tension in each of the cables is the same and then calculate this tension when the container is being lifted at a constant velocity. Well, the weight will be shared equally between the 4 cables. So the tension is equal to the weight of the container, which is mg, over 4, as there are 4 cables. The mass was 22,000 kilograms, the gravitational field strength 9.81 newtons per kilogram, giving a tension of 5.4 times 10 to the 4 newtons. In part 2, we need to calculate the moment of the container's weight about the pivot point Q, which is 32 meters from the container. Well, for this, we use moment is equal to force times distance, the force being the weight of the container, its mass, multiplied by the gravitational field strength, multiplied by the perpendicular distance from point Q, which is 32 meters. This gives a moment of 6.9 times 10 to the 6 Newton meters. In part 3, we need to describe and explain a feature of the crane which prevents it from toppling over when lifting a container. Well, the counterweight is providing an anti-clockwise moment about Q. This opposes the moment of the container and prevents the crane from toppling. In B, we're given the cross-sectional area of each cable at 3.8 times 10 to the minus 4 square meters, and in part 1 we need to calculate the tensile stress in each cable. Well, stress is equal to force over cross-sectional area. The force is the 5.4 times 10 to the 4 newtons found earlier over the area given. This gives a stress of 1.4 times 10 to the 8 newtons per square meter, or pascals. In part 2, we're told the unloaded length of the cables is 25 meters, and we need to show that the cables extend by 17 millimeters when lifting the container, given the Young modulus of steel at 2.1 times 10 to the 11 pascals. Well, Young modulus is equal to stress over strain, which we can write as Young modulus E is equal to the stress, force over area, divided by the strain, change in length, over original length. We can rearrange this as the Young modulus is equal to force times length over area times change in length. We want the change in length, which is equal to the force times the length over the area and Young modulus. We can now put in the values given, and this gives a change in length of 0.017 meters, or 17 millimeters as required.